Hi everyone, my name is Ubaidullah Hafiz and today I am going to talk about Pesto, which is an optimal placer and scheduler for DNN operations in DNN training. This is a joint work with Xiao San, my advisor Dr. Anshul Gandhi and Professor Zanua Liu from Stony Brook University. There is huge disparity in memory footprint of training modern DNNs and memory available in a single commodity GPU. Graph on the right side shows memory footprint for training some of the modern DNNs. Graph shows that most of the modern DNNs require more than 32 GBs of memory, with GPT-3 requiring a training memory footprint of around 700 GBs. However, the maximum memory available in a single commodity GPU these days is 32 GBs. Just to give a quick reference, the brown dotted line in the above graph shows where the maximum memory of commodity GPUs lies. This clearly shows that most of the modern DNNs are unable to fit within the memory of single GPU and must be split across multiple GPUs, which is called model parallelism. Expert placement is one of the most popular strategies for model parallelism. Expert placement make use of the fact that DNNs consist of multiple layers of operations which are linearly stacked. Expert simply places a subset of these layers on each available GPU. Here is a high-level graph of NASNet model, which is a CNN used for image recognition. Expert simply places a subset of these layers on each GPU. This is how expert placement for NASNet looks like across 3 GPUs. Expert is an easy-to-use strategy, however, it has a few weaknesses. GPU utilization for expert placements is typically low. Expert placements also incur significant GPU-GPU communication overheads. Another more aware strategy of model parallelism is to use learning-based algorithms. Learning-based algorithms use strategies like RNNs and hierarchical models, etc. Learning-based algorithms are able to find placements which increase GPU parallelizability and reduce training time as compared to expert placement. This is a graph of neural machine translation model. Color of each node in this graph shows device assigned using colloq RL, which is a reinforcement learning-based placement technique. These placements enable higher GPU parallelizability as compared to expert. However, learning-based algorithms typically takes multiple hours and sometimes even days to find placement. In the rest of the talk, for simplicity, I will call the time to find placement as placement time. This leads us to our problem statement. We want to design a DNN graph placement strategy which can find close to optimal placements. For this placement strategy, the placement time should be non-prohibitive and should not be order of multiple hours. We present our solution Pesto, which treats each DNN training job as a data flow graph and models placement and scheduling of DNN training as a graph partitioning problem. Let's discuss a few more details about Pesto. Pesto models DNN placement and scheduling as a graph partitioning problem. First step is to estimate the compute time of each node in the graph, which is also called an operation. Next, Pesto estimates the potential communication overhead each edge can add. Then we reduce the size of the graph by using specially designed graph coarsening algorithms, details of which can be found in the paper. Last step is to use the ILP and list scheduling algorithms to find placement and scheduling of DNN operations. Another important thing to note here is that the edges with adjacent nodes placed on the same device won't add any communication cost. This is a high-level picture of integer linear programming used by Pesto. Highlighted part shows that the number of constraints in the ILP is directly proportional to the number of operations in the graph, which is typically order of thousands. Pesto uses graph coarsening algorithms to reduce the number of nodes in the graph, hence reducing the number of constraints, which ultimately reduces the solution time of ILP from multiple hours to a few minutes. This concludes our discussion of design of Pesto. To evaluate Pesto, we compare performance against multiple baselines. We compare Pesto against Expert, which is an easy-to-use strategy and places a subset of DNN layers on each of the available GPUs to satisfy memory constraints. We also compare with Bechi, which is a heuristic-based approach. For all the models we experiment with, Beiti is able to find placements in less than 3 minutes, which is very fast. Beiti has multiple heuristics to use. However, for all our experiments, a modified version of small communication time heuristic performs better than all other heuristics. So we report comparison numbers only with MSCT. The graph shows per step training time for multiple models, each with 3 different placement techniques. We experiment with transformer model, NASNet, RNNLM, and NMT. For each of these models, we tried multiple variants resulting in 11 different configurations. For all of these configurations, training time with Pesto as the placement technique is less than both expert as well as Page. On average, Pesto is able to reduce training time by 14% as compared to best of expert and Page. Another important observation is that expert fails to stick to memory constraints for 2 of the variants of NASNet, resulting in out-of-memory error. However, both Beijing and Pesto are able to find placements which do not violate memory constraints, showing their superiority over expert placements. Non-trivial reduction in training time achieved by Pesto are due to its ability to find placements with high GPU compute parallelizability and superior scheduling, which overlaps cross-device communication with compute, hence mitigating communication overheads. Training time shows one side of the picture. Now we compare placement times of different placement strategies. Table shows the placement times of 4 different techniques. Beiti has the lowest placement time and is able to find placements in less than 3 minutes for all the models. RNN-based and Pesto are learning-based strategies and can take multiple hours and even more than a day in some cases. Placement times of Pesto are higher as compared to Beiti, but are well within 1 hour and hence significantly lower than learning-based strategies. Pesto achieves these relatively small placement times because of the graph Gaussian algorithms, which reduce the number of constraints in the ILP. To compare the total training effort of different placement strategies, we look at the summation of total training time and placement of each strategy. This table compares the total training effort for 4 different strategies relative to expert placement. On average, Pesto is able to reduce total training effort by 20% as compared to expert, which is significantly higher than all other strategies. To conclude, Pesto is a DNN operation placement strategy which can find non-trivial placements of DNN training graphs in just a few minutes. Pesto is integrated with TensorFlow and is open sourced. Pesto works out of the box without requiring to modify any user level code. Thank you all for listening. Let me know if you have any questions for me. In this later part of the talk, we will go over some interesting details involved in designing Pesto as well as integrating it with TensorFlow. This part of talk is divided into 2 sections. We first discuss some details about TensorFlow, which is a popular DNN training framework. And then we talk about design and implementation challenges involved in implementing Pesto and its integration with TensorFlow. Let's start with TensorFlow. TensorFlow is a popular DNN training framework. TensorFlow provides all the tools needed for the entire DNN training pipeline, starting from pre-processing data all the way to training modern DNNs on enormous data sets, and then finally serving these models for inference. TensorFlow offers high-level APIs, which are easy to use and does most of the heavy lifting for the program. One can write a DNN training pipeline by writing just a few lines of code. TensorFlow models DNN training jobs as a data flow graphs, which is quite natural for such jobs. Let's discuss data flow graphs in a little bit more detail. Not just TensorFlow, other popular DNN training frameworks such as PyTorch also treats DNN training computations as data flow graphs. The figure on the right shows an example of data flow graph. Each node in the graph represents a computation operation, and the number inside each node represents the cost of executing the given computation. Each operation is executed on a compute device, which is typically a CPU or a GPU. Edges in the graph represents data flow. Edge can result in additional communication cost if adjacent nodes are placed on different devices. Magnitude of this communication cost depends on the underlying hardware. Generally, all the data flow graphs tend to be directed acyclic graphs or simply DAGs. This figure is very simplified example. For the models we experiment with, each graph contains thousands of nodes. If the hardware specifications, that is CPU, GPU models, etc., are known, compute cost for the operations in a DNN graph are highly consistent and predictable across multiple runs. The graph on left shows the normalized standard deviation in the compute time for all the operations that were executed on the same GPU device. Graph shows that on average across the 4 models we experiment with, 90% of operations have less than 10% normalized standard deviation. Further analysis shows that the operations with higher standard deviations are the ones with very low compute times, which is of the order of few microseconds. For this plot, we use data from running each DNN training model on the same underlying machine 1,000 times. Similar to compute operations, the amount of communication overhead each edge can add is also very consistent and is thus highly predictable. Typically, the magnitude of communication is directly proportional to the amount of data being transferred. This graph on the right shows how the communication time varies with the amount of data being sent across each pair of devices. The strictly linear trend clearly shows the consistency of communication time with respect to the amount of data being transferred. This ability to consistently predict time for each data flow and compute operations in the graph is the baseline assumption for Pesto to be able to find placements and scheduling, which can reduce training time significantly. Next, we will talk about both the algorithmic as well as the implementation related challenges that Pesto addresses to actually do the placement and scheduling for DNN training jobs. DNN graph scheduling is different than how graph partitioning problem is modeled in classical literature, and hence no existing algorithms can be used as it is without careful modification. First, let's talk about considerations involved in modeling communication across devices in DNN training. While modeling communication for DNN training, congestion and disparity in communication links must be taken care of. Congestion arises when more than one operations are ready to send over the output of data to be used by operations waiting to execute on a different device. While modeling communication, we need to address the fact that all the DNN operations share the same links and must be modeled according to the sharing mechanism in place inside the hardware of the machine. GPU communication links can have different bandwidths as compared to the communication links between GPUs and CPU. While modeling, this must be taken care of to avoid unexpected results. There are multiple factors that needs to be addressed to make sure Pesto picks placements which ultimately reduce training time as compared to naive placements. Suboptimal placements that do not exploit parallelizability of GPUs can lead to significantly higher compute. Each operation in DNN has some memory requirements. If we place a set of operations on a GPU, total memory of which is higher than the memory available on that GPU, DNN training would fail and result in an error. Pesto takes care of this while doing placements to avoid such errors. Sometimes DNN training graphs can contain subsets of operations that needs to be placed on the same device. Otherwise, training would fail. Pesto also takes these constraints into account while finding placements. Let's discuss how exactly Pesto addresses these challenges. Modified version of list scheduling algorithm is employed by Pesto to take care of communication constraints. Constraints in the ILP are carefully set up such that they don't add significant overheads and address all the constraints involved in placement of compute operations. Lastly, Pesto uses novel graph portioning techniques to reduce ILP solution time, ultimately reducing Pesto's placement time. After finding placements and scheduling for the DNN graph, next step is to enforce these strategies in TensorFlow. In TensorFlow, tf.graph API contains information about the structure of the control flow graph. Inside tf.graph, each operation is represented by an object of class tf.node. Pesto enforces placement of operations by using setAssignDevice function of tf.node class. To ensure that operations are executed in the order as dictated by ILP and list scheduling combined, Pesto use add control dependency function to add scheduling constraints, which is also available in tf.node class as a part of vanilla TensorFlow code. Another important consideration here is that Pesto modifies TensorFlow source code to enable users to provide placement and scheduling directives as a side input to the user code. Hence, the users can employ Pesto without modifying their code. Thank you for being here. If you have any follow-up questions, feel free to email me, and I will try my best to get back.